Good afternoon, everyone. Welcome to the 12th problem solving session in the course Chemical Engineering Thermodynamics. So, today we are discussing about the chemical reaction equilibrium. So, till now, what we were discussing was initially what are the equation of state for real fluids and then system of fluids, whether it's liquid or liquid gas, and when they are in equilibrium, and how is it defined, the chemical potential equilibrium. So that way, we were discussing between the two different phases, and then how will it be changing? What will be the boiling points and all? What are the mixing properties? All that we have discussed. So now we are coming to the reactions in the system. Then what will happen? So you assume, uh, talking about the reaction coordinate, assume there is a reaction. A plus BB gives CC plus DD. Okay. Uh, and we define something like an extent of a reaction. Okay. Extent. And if it's reversible, you can write it in the other way. CC plus DD gives BB plus AA. With one more extent of the reaction as epsilon 2. So it can, what is forwarding, what is reversing, both will have two different extents here. Okay, right. Then how do we define the extent of the reaction is, so generally we define extent in terms of how many number of moles of some reactant has reacted. Okay, like we have defined here, epsilon is equal to Ni naught minus Ni by mu I, where this is stoichiometric coefficient. Okay, stoichiometric coefficient. For example, if we consider the first equation here, now Na naught, uh, and Na naught minus Na by minus Na. Sorry, by minus A, which is a stoichiometric coefficient for the reaction A. So for this is for a single reaction. This is actually written as Na minus Na naught by A, and this is less than 0. So it is getting reacted, right? So what will be the extent is minus 5 moles has reacted, something like that. Okay. So if we, so what does this stoichiometric coefficient play the role here? Okay, to understand that, assume, okay, assume there is a reaction, two-way gives 5C. Okay, two-way gives 5C is there. Then epsilon is given, for example, initially I had 50 moles of A. And then now finally I have 40 moles of A. By the stoichiometric coefficient is minus 2 for A. So what will I say? The extent is minus 5. That is 5 moles of 5 times of this reaction has happened. In that way, I can say actually 10 moles of A has uh, reacted with have been born. Okay, but actually, if we consider go for this reaction, then extent is minus 5. If the same reaction I write it in this way, then A gives 5 by 2C. Then what will I say? 50 minus 40 by minus 1 is there, right? So I will have minus 10 extent. Extent is equal to minus 10 here. So the trick is here you can by from the extent of the reaction you can also tell what how many number of moles of the C is produced here. Okay, so this is equal to the same extent is equal to number of moles of C produced by its stoichiometric coefficient. Okay, initially assume number of moles of C were here. Okay, NC naught minus NC by C equal to NA naught minus NA by A minus A. Okay, is stoichiometric coefficient. So these both are equal. So when I come to NC naught I'm assuming 0, then minus NC by C. That is this. Okay, this is minus 5. This is minus NC by C. So now NC equal to 5 into 5, 25. No, I think you understand, right? Okay. When uh, 10 moles of A has reduced, 25 moles of C are produced. Okay. 10 gone, 25 gone. Okay. 1 gone, 5 by 2 is coming, right? 10 is 5 by 2 into 10. Okay. 5 is 25. So extent is helping us to write the dynamics for each of the component in a reaction. So if I have multiple reactions like this, for example, I have A1, A plus E, E gives FF, then okay. To define what is the mole fraction of the A in whole mixture, I will write like this. Okay. This is suppose for a single reaction. Yi is equal to Ni by N. This Ni plus Vi into epsilon. Okay, this is derived from this reaction. So, stoichiometric coefficient into epsilon plus Ni. Okay. Minute. I think okay. Okay, okay, okay. I have written it in the wrong way. Okay. Sorry for the mistake. Greater than. So extent is like how many moles has reacted. Okay, it's plus only. Okay, sorry for this. Yeah. Hmm. Okay, so this is there. So Ni I'm defining as Ni naught plus mu I into epsilon. And similarly for the total number of moles, this is the total number of moles. So N naught is equal to sigma of Ni naught, whatever summation of each component number of moles. Okay. And here mu is the total stoichiometric, net stoichiometric coefficient for the reaction. For multiple reactions, as I explained here, if I have one more reaction, including the A, then I will write A minus A1. Okay, A into epsilon 1 minus A into epsilon 1 minus A1 into epsilon 3. I will write like this here. Okay, Na naught minus A epsilon 1 minus A1 epsilon 3. And the units are balanced here because the units of epsilon is number of moles, okay? Moles only, that's why. Now, right, I think like you have gone through the lectures also. Just for clearer explanation, I have described the ideal one. Now, criteria for equilibrium is mu I into mu I is equal to 0. And the reaction constant, okay, is written in terms of fugacities of the each component in the system. Okay, where Fi cap is the fugacity of species I in the mixture, and Fi naught is the fugacity at standard state. Okay, at some temperature, at some standard temperature, you know the value, then you will take from that value. And also, K is the equilibrium constant, which is defined in terms of the change in Gibbs energy of the reaction at the standard state you consider. Okay. Now, coming to the K here, we know this at the standard state, right? And again, this is equal to delta H naught by RT square. This is the basic relation we have been studying in so long. Now I am representing this delta G naught by RT as ln of K. Now I have this equation, or it can be written in this terms, okay? When I take the T square there. Then if I integrate this equation, I will be getting ln of K by K1. So if I integrate from K1 to K like that and T1 to T, then I am getting this equation ln of K by K1 is equal to delta H naught by R 1 by T minus 1 by T1. So here, if I know K at, if I know K at some K1 at some T1, I can find K at some temperature T. Okay, this is the usage of this issue here. Now, coming to the only gas phase reactions, how can this fugacity be represented? Okay, it can be written in terms of fugacity coefficient into mole fraction. Power to the power the stoichiometric coefficient is anyway there, and this uh, this is P by P naught power uh, minus V. Okay, so this is when this is an ideal solution, then this is equal to phi I only. Okay. And if it is an ideal gas behavior, then it goes to equal to 1. So this is what we will be using in so many systems. Okay. Now we'll be discussing few questions. The first question, yeah, the extent of a reaction is different for reactants and products, dimensionless, dependent on the stoichiometric coefficient, and all of the above. No, because I discussed earlier, right? Epsilon equal to Na naught, Na minus Na naught by minus A equal to Mc minus Mc naught by C. So I have discussed this. So it is not it's different for reactants in products. It's the same. And dimensionless I have written. But I have told already that epsilon has unit of moles. That's why it is not dimensionless. Dependent on the stoichiometric coefficients. Yes, it is dependent on. So N9 minus N9 naught by mu I. Epsilon is equal to this. So this is the correct definition. So it depends on the stoichiometric coefficient. Right? The equilibrium constant K for a chemical reaction depends on temperature only, pressure only, temperature and pressure, ratio of reactants. So what we know is K is equal to exponential naught minus delta G naught by RT. So delta G naught it depends from the reaction and it depends only on the temperature. So temperature only. Okay. For a reversible exothermic gas phase reaction, A plus B gives reversible now. Reversible gives C. Equilibrium conversion will increase with. So here it is given it's an exothermic gas phase reaction. So exothermic means delta H is less than 0. Right? Okay. Okay. So this is a gas phase reaction, right? So what do we have for gas phase reaction? Product of yi over vi mu I, the LCI, equal to p power minus mu and k. And what is mu equal to -1 -1 plus 1. This is right equal to -1. So this is given as P into K. So what will happen if I increase pressure for this validation for this equation? The Y will also increase, right? And in that this K can be written as exponential of minus uh, delta G naught by RT. So okay, so here if I increase temperature, the K will decrease. And then Y will also decrease. Or the ulta way, if I decrease the temperature and K will increase and Y will also increase. So here we have increase in pressure, equilibrium conversion will increase. Okay, the conversion increases. And we need decrease in temperature, right? So when it is increase in pressure, decrease in temperature, this is so when this happens, the equilibrium conversion will increase. Okay. For an exothermic reversible reaction, which one of the following correctly describes the dependence of the equilibrium constant with temperature T and pressure P? So we have this equation, right? It is saying describe the dependence of K with temperature and pressure P. So I remember this equation, right? Ln K by K1 equals to minus delta H by R 1 by T minus 1 by T1, right? So for an exothermic reversible reaction, this is negative. So if I increase the temperature, K is going to decrease. Right, this will whole magnitude will decrease, and that's why K will decrease. So K decreases with an increase in and it is independent of pressure. Okay, right? Now a gaseous system contains H2, I2, and HI, which participate in the gas phase reaction given as 2HI reversible H2 plus I2. At a state of reaction equilibrium, the number of thermodynamic degrees of freedom is. So F is equal to C minus P plus 2 minus N minus S. Right, we have discussed this in the last week session. So here number of components, it is 1, 2, 3. 3 minus completely happening in one phase only, right? Gas phase. So 1 plus 2 minus 1. 1 independent constitutive reaction equals to 3. So that is P comma P comma Y we should be knowing. R, R, L1. Okay. So the answer is 3. Next question. The reaction A in liquid phase is equal to I should say yes, okay. R at gas plus S at gas is allowed to reach equilibrium conditions in an autoclave. At equilibrium, there are two phases. One a pure liquid phase of A and the other a vapor phase of A, R, and S. Initially, A alone is present. The number of degrees of freedom are. So, here I have number of components are 3 minus 2 phases are there plus 2 minus 1 reaction is there equal to 2. And these are temperature and pressure. Because anyway, the mole fractions are connected between the two phases. Okay? So coming to the seventh question, here we have dou G by dou Ni. So you remember that Mi bar is equal to 2m by dou Ni. Then when the M is G here, then it is called mu I, and this is called the chemical potential, right? Then um, we see one more thing here. The exponential of minus delta G by RT is equal to K. So this is equal to the reaction equilibrium constant. And this Ni d mu I is equal to 0. That is Gibbs to Hem equation. The one more option here is Arrhenius equation, which is K is equal to A power minus E by RT. That is Arrhenius equation. So this is not matching. So we have P3, R2, and S4 here. Okay. Coming to the next question, the enthalpy of formation at 298 Kelvin, delta HF naught of CO2 and PBO are minus 393 and minus 220 respectively. The enthalpy change for the whole reaction is what? So, we have studied that delta H of a reaction equals to delta H formation of the product minus delta H formation of the reactant, right? So here we have the products are PB and CO2. So since PB is it's in standard state, in the solid state, so 0 plus the CO2 has a formation of 3 minus 393. So minus 393 minus delta H formation of PBO. So 2 into the PBO has a minus 220. So minus 220 and minus the C also is in standard state. So this. So after summation, we are getting 440 minus 393 equals to 47 kilojoule per mole. Sorry, we have multiplied with the number of moles. So kilojoule only, okay? So 47 kilojoule. Right. Next question. At a given temperature, K1, K2, and K3 are the equilibrium constants for the following reaction 1, 2, 3, respectively. So K1, K2, and K3 are related as. So we have to look into how these three reactions are related as. Okay. So we can see 3H2 plus H2 gives 4H2. Okay. And we'll see this how equation 1 plus equation 2 will behave. Okay. Equation 1 plus equation 2 will give us CO plus CH4 plus 2H2O is CO plus CO2 plus 4H2. And this will give us CH4 plus 2H2O reversible CO2 plus 4H2. And this is the reaction 3. Right? So that's why we have delta G3 equal to delta G1 plus delta G2. So we know minus RT ln K3 equals to minus RT ln K1 plus minus RT ln K2. Okay, from this we get K3 is equal to K1, K2. Okay, right. Now we have 2 copper K plus 0.502 is CO2O, and again same CO2O can be obtained as 2 copper in liquid plus 0.502 gas. This. So in different phases of CU. Okay, different delta G naught is there as a function of temperature. The molar change, free energy change is delta G at 1300 Kelvin for the transformation of solid Cu to liquid Cu will be. So if I want Cu S to Cu liquid, how will I get this? 1 minus 2, right? If I do 1 minus 2, I'm getting this. 2 Cu solid to 2 Cu liquid. I'll get this reaction. So that's why I will have 1 minus 2 by 2. Okay, equal to the delta G. If I do, I'll have minus 162200 plus 188300 and plus 88.48 minus 69.24 into 1300 whole by 2. This gives us 1085 by 2 equal to 544 joule. Okay, this one, right? I think you understood. Okay, now, so from these questions, what we are understanding, okay, I just want to press on the thing that if we know delta G naught or delta HF or delta H for some known reaction, then we can find the same energy properties for some unknown reactions. Okay, using this relations between the delta G naught or delta H. Okay, right. At standard conditions, N2 plus 2O2 gives 2NO2 and NO plus half O2 gives 1NO2. The standard free energy of formation of NO. So formation of NO element. Okay. So we want we want to okay. We have to subtract this, right? Okay. We will do one equation 1/2. Okay. gives us half N2 plus O2 is NO2. And the equation reaction 2 is NO plus half O2 gives NO2. And if I subtract, I'm going to get uh, half N2 plus O2 minus half O2 gives me NO. Okay, so this is how I'm getting the NO into the RHS so that I'll find the delta G formation of the NO. Okay, so this is half N2 and mm, plus half O2 giving me NO. How did I get this reaction? I got this reaction by half of equation 1 minus equation reaction 1 and reaction 2. So which is given by delta G is given as um, half of equation reaction 1 is 100 kilojoule minus minus 35, right? So giving us um, half oh sorry, yeah. So this half of 100 is actually 50 here. That is what I'm searching. Where did I make the mistake? Yeah, 50 minus 35. And this is 85. Okay, right. Okay, coming to the next question. A vessel initially contains a not mole of water vapor only if the composition of water vapor occurs according to the reaction giving H2 plus half O2, the fractional decomposition of water vapor in terms of the reaction coordinate epsilon is equal to. So what is the fractional decomposition of the water? We generally give Yi equal to Ni by N naught equal to Ni naught plus Y epsilon by N naught plus mu epsilon. Here mu is equal to -1 plus 1 plus 0.5 equal to 0.5. So for H2O, YH2O, if I write here, initially there were N naught things, right? So N naught minus NH2O. At some time, what will be H2O? It will be N naught minus epsilon. Minus 1 stoichiometric coefficient is there, right? That's why. right? Hmm. This is sorry, I have written wrong. Fractional decomposition. So completely N naught moles should be decomposed. How much decomposition has happened till now is the initial minus current by total. How much it can happen. So this is given by epsilon by N naught. Okay. I hope it is clear here. Please go through it. So, fractional decomposition. Okay. For a system in which the following reaction occurs, that is CH4 plus H2O giving CO plus 3H2. Assume there are present initially 2 mole of CH4, 1 mole of H2O, and 1 mole of CO, and 4 mole of H2. Okay, I'm writing N not equal to if I write CH4, H2O, CO plus 3H2 is given as 1, I'm sorry, 2, 1 and 1 and 4. So total it is 5, 6, 7, 8. So 8 moles are there. And if I come to stoichiometric coefficient, here it is minus 1, and 3. So 3 minus 2, 1, plus 1, 2. So total is 2 equal to 2. Okay. Now, what has been asked? That is what. So, for the reaction coordinate, epsilon is equal to 0.5. Epsilon is equal to 0.5. It implies it is equal to N by, sorry, 1. Yeah. The mole fraction is maximum for what and minimum for what. So, if I compute the mole fractions, for CH4, it will be 2 minus epsilon, okay, by 8 plus 2 epsilon. So how 8 plus 2 epsilon is coming is N naught total is there, right? N naught plus mu epsilon is giving this. Mu is completely 2 epsilon. For H2, if we write, initially 1 mu was there, minus epsilon by 8 plus 2 epsilon. And similarly for CO, 1 plus epsilon. The stoichiometric coefficient is plus 1 by 8 plus 2 epsilon. And for this, 4 plus 3 epsilon by 8 plus 2 epsilon. And if I compute for epsilon is equal to 0.5, what are these values? For this, I'm going to get 0.16, 0.056, 0.16, and 0.61. So the maximum is for H2. H2, okay. And the minimum is for the H2O, this one, right? So now, initially we were writing and learning about degrees of freedom. Then we learned about how to write this delta H formation, adding reactions, subtracting reactions, and getting for one of their product, one of the reaction, something like that. And then how much extent of the reaction is happening. Now, how much, what is the composition of the mixture after some time that we will have discussed. Okay, and this is we are looking into the questions. The next question. A gas mixture containing 3 mole CO2 H2, H2O, CH3OH, and CO. Okay, these are the 5 components here. Develop expression for the mole fraction of the species in terms of the extent of the reaction. So initially, how much were there? CO2 3 were there, H2 5, 1 mole of water, and these are 0. And if I go for in the reaction 1, if I go CO2, it has -1, H2 has -3, H2 has +1, CH3OH +1, and CO is not produced anywhere in the reaction. And coming to the reaction 2, we have CO2 is -1, -1, +1, 0, +1. Okay, total if I say this is 5, it's an 8, 9, and this is -4 plus 2 minus 2, and here -2 plus 2, 0. Okay, for the reaction 1, assume epsilon 1 is the extent, and for the reaction 2, epsilon 2 is the extent. Then when I write yi for each of the species, then CO2 initially was 3, okay, minus epsilon 1, minus epsilon 2, by total is 9 minus 2 epsilon 1. Okay, total in my not 9 minus 2 epsilon 1 plus 0 epsilon 2. That's how this is there. Okay, for H2, 5 minus 3 epsilon 1 minus epsilon 2 by 9 minus 2 epsilon 1. For H2O, 1 plus epsilon 1 plus epsilon 2 by 9 minus 2 epsilon 1. This is for the H2O. Okay. If I write Y, CH3OH equals to 0 plus epsilon 1 by plus F0 epsilon 2 by 9 minus 2 epsilon 1. And YCO is given as epsilon 2 by 9 minus 2 epsilon 1. Okay. Okay, coming to the next question. The water gas shift reaction CO plus H2O gives CO2 plus H2 is carried out at 1100 Kelvin at 1 bar with 1 mole of H2O vapor and 1 mole of CO present initially. So, as we were doing, CO, H2O, CO2 and H2. So, what comes CO 1 mole and H2O 1 mole, 0, 0. The equilibrium constant of the reaction is found to be equal to 1. So, K equal to 1. If the reaction mixture behaves as an ideal gas, the fraction of steam that reacts is. So, now we are coming to discuss how we can write. So, till now we have learned how to write the yi, right? So, from yi, we have an equation relating to the equilibrium constant, that is yi power mu I product to A equals to k into e power minus mu. Now, if I write mu, suppose u minus 1 plus 1 and plus 1. So, if I see total, this is 2, this is 0. Okay. Now, if I write, go for writing my, then my total is 2. Okay. And overall, the change in number of moles is 0, whatever reaction happens, right? So by 2, and this is 1 minus epsilon. And here also 1 minus epsilon by 2. This is epsilon by 2. And for H2, it is epsilon by 2. Now, when I'm writing this equation, the product will be y CO2 into YH2 by YCO into YH2O equal to K into T power minus 0. So this is equal to 1 and K is equal to 1 given. Therefore, we have to find the epsilon here. Then this we can write as 1 minus, sorry, yeah, this is epsilon square by 1 minus epsilon whole square equals to 1. It implies 1 minus epsilon is equal to epsilon. This is the square root is taken. We can not have, if it is 1 minus epsilon is equal to minus epsilon, it is not true. Therefore, 1 minus epsilon is equal to epsilon. Therefore, epsilon is equal to 1 by 2. That is the reaction mixture behaves as an ideal gas. The fraction of steam that reacts is. So 1 by 2 mole of the 1 mole initially. So 50% only, right? That's why half. If I say it was 5 moles here and now this there's a 2 moles, then it will be 2 by 5 or 2 by 3 if it is 3 moles, like that. Okay. Next question. The water gas shift reaction, the same reaction as above. Uh, um, 1 mole of H2 and 1 mole of CO. Here epsilon is already given. The initial reactants mixture contains 2 mole of N2 along with this. Then fraction of the steam is what? Okay, N2 is 2. Now total N naught equal to 2 plus 3 plus so 4. Right? Then if you see in the last equation, the same nu I is there. Okay. Minus 1, 1, 1, and 0. And total is 0 only. And just the yi here changes here. Okay. 1 minus epsilon by 4, 1 minus epsilon by 4, epsilon by 4, epsilon by 4, and 2 by 4. That is 1 by 2. Okay. But when I go for writing this K equals to YCO2 YH2O by YCO to Y. If I go for this, then what will I have? The same thing. Okay. This will be the same. Epsilon. This H2O. Okay. This will type now. Epsilon square by 1 minus epsilon square. Okay. The denominator has changed here. But finally, if we solve this also, epsilon is equal to 0.5. Okay. Right. But if it's some other reaction where there is some other y, then it will be changing. Okay, here it is getting cancelled everywhere. That's why there is not much problem in this system. Okay, fine. 17. The reduction of FeO and CO gas in co-current fluid is given by the following equation. Yeah. Okay, so FeO plus CO gives us Fe plus CO2 and the delta G naught equals to 8,120 joules at the given temperature. Now, the ratio of PCO2 for this reaction at the same temperature is what? So, okay, when we have this delta G naught, we can have the relation minus RT and then K equal to delta G naught. R is equal to 8.314 joule per mole Kelvin. If I substitute here and T equal to 1.73 Kelvin, then I will get K equal to 0.435. Okay. From this now I have the relation K e power mu equals to 5 yi power. Actually, this is f I cap power mu I. right? This is equal to YCO2. Here only these are the gases. Okay, solids are not gases. See, yeah, Fe and Fe are not gases here. So I am writing this as YCO2 into P by YCO into P. This is power 1, power minus 1 is there. That's why this can be written as PuCO2 by PCO equal to K 0.435 into P into power nu, which is completely equal to 0 here. So equal to 1. Therefore, I have PCO by PCO2 is 1 by 0.435, which is equal to 2.8. Okay. Now we have come to heterogeneous reactions. Earlier it was all one phase reactions. Now we have went for heterogeneous reactions also. Coming to the next question. Vapor phase hydration of C2H4 to ethanol by the following reaction. Attains equilibrium at 400 Kelvin and 3 bar. Standard Gibbs free energy change of reaction at these conditions is delta G naught is equal to 4000 joule per mole. For 2 moles of an equimolar feed of ethylene and steam, equation in terms of extent of reaction at equilibrium is what? So ethylene equimolar feed. Okay. 2 moles of the whole feed is there. So N naught equals to 2, right? And mu is equal to 1 plus, I'm sorry, minus 1 plus minus 1 plus 1 equals to minus 1. And so I will be writing the y as YC2H4 equal to 1 minus epsilon, by total is 2 minus epsilon. Okay. Here initially C2H4 was in C2H4 not 1 and H2 not equal to 1 and equimolar 2 moles of feed. Okay, and total 2 minus epsilon is there. Y H2O equal to 1 minus epsilon by 2 minus epsilon. And Y C2H5OH equals to epsilon by 2 minus epsilon. Now, considering this, if I write this equation as pi of y power vi is there equal to p into p power mu into k. So here we have that what do we know? Wait, the LHS is equal to YC2H5OH by YC2H4 into YH2O. see, if it is this 2 here, then here YC2H4 square will come. Okay. I think I'm making it clear. Yeah. Equals to epsilon by 1 minus epsilon square into 2 minus epsilon. Okay. This is the LHS. Coming to the RHS, this is equal to minus 1. What is the K? So we here know delta G naught is equal to 4000 equal to minus RT and then K 400 ln K. Okay, this T is equal to 400 Kelvin. If you solve this, R is equal to 8.314, then you will get K equals to 0.3. Okay, now if I substitute all these things into one thing, then P power minus 1 minus of minus 1 into K equal to epsilon 2 minus epsilon by 1 minus epsilon square. Sorry, here it is minus. Sorry. This. That's why this is equal to 0.3. This is equal to here it is given 3 bar, right? So 3 bar. Therefore 0.9 is equal to epsilon 2 minus epsilon by 1 minus epsilon square. So, yeah, this one, D option. Right? Okay, next. Calculate the fraction of pure ethane that would dehydrogenate at 750 Kelvin and 5 atmospheres. If the following reaction goes to equilibrium, delta G naught for the reaction is equal to this. What do we have to calculate? Calculate the fraction of pure ethane. Here, this is ethane. This is ethene. Okay. So YC2 at 6 equal to what? So first we need to find out what is epsilon based on that only. Okay. So assuming 1 mole of ethane was there initially, now I will write YC2 6 is equal to 1 minus epsilon by totally 1 moles were there initially, and the mu is equal to minus 1 plus 1 plus 1 equal to plus 1. So 1 plus 1 by 1 plus epsilon. And for YC2H4 equal to epsilon by 1 plus epsilon, and YH2 equal to epsilon by 1 plus epsilon. Now, from the delta G naught, I will get delta G naught is equal to minus RT ln K at temperature 750 Kelvin. Now, from this, I will be finding K equals to yeah, I have done. Yeah, K equal to 0.9932. Okay. And you have this equation p power minus nu, that is minus 1 into k, that is 0.9932 equals to this is equal to epsilon square 1 plus epsilon into 1 minus epsilon. And upon substituting 5 bar here, when you solve, the epsilon is equal to 0.4. That is what you get. Finally, you will get YC2H6 equals to 1 minus 0.4 by 1 plus 0.4, which you can calculate here as 0.428. Okay. Yeah. I think by this time you are very clear with what type of calculations we are making here in all these questions. It is very easy to understand, I guess. So yeah. For a gas phase cracking reaction, A gives B plus C at 300 degrees Celsius. The Gibbs free energy of the reaction at this temperature is delta G, so and so. The pressure is 1 bar and the gas phase can be assumed to be ideal. The universal gas constant is this. The fractional molar conversion of A at equilibrium is. So yeah, delta V naught is given minus RT ln K. On substituting everything, we will get K equals to 1.78. Okay. Now, so K is equal to 1.78. We can find out here. And similarly to the last thing, A, B, C, initially assume there is 1, 0, 0 and not, and this minus 1, 1, 1. And at equilibrium, the yi I can be written as 1 minus epsilon by total and total is 1 and this mu is 1. So 1 plus epsilon, here also 1 minus, sorry, here it is product epsilon by 1 plus epsilon, epsilon by 1 plus epsilon. Now going to the equation e power minus v k equal to yb yc by ya, which is equal to epsilon square by 1 plus epsilon into 1 minus epsilon. And here I have put k is equal to 1.78 and p is equal to 1 bar. So upon solving this, I will be getting epsilon is equal to 0.8. So the fractional molar conversion of A at equilibrium is 0.8. Okay, right. And the last question we are discussing. The standard Gibbs free energy change and enthalpy change at 25 degrees Celsius for the liquid phase reaction. Here, this is L here, okay? It's confusing one, but this is L. The liquid phase reaction are given as minus delta G naught and delta H naught are given. The solution is ideal and enthalpy change is assumed to be constant. Equilibrium constant at 95 degrees Celsius. So 298 Kelvin is given. Okay. So since I have a delta G naught, I can find K at 298 Kelvin equal to exponential of minus delta G naught by RT. This is same as minus RT ln K equal to delta G naught. Okay, the same thing is there. Now, if I'm putting this exponential of 4650 by 8.314 into temperature is 298. If I do this, then I'm getting K at 298 Kelvin equals to 6.53. Right? Now, this information is just given for the distraction here. Now I have ln, no, sorry. Yeah, I have one more equation, which is ln K by K1 equal to minus delta H by R 1 by T minus 1 by T1. Now, I know this equal to 6.53. I want to know this. Delta H is given, R is known, and temperature T is 95 plus 273, and T1 equal to 25 plus 273. Which is actually 298. This. So upon solving this equation, you will get K at 95 degrees Celsius equal to 4.9, which is equal to this option. So this is what we have discussed, chemical reaction equilibrium. We can initially we learned how to write the total number of moles, stoichiometric coefficient, what is their importance, what is the dependence on temperatures or pressures, and finally we learned how to write the extent of the reaction, followed by how to write the mole fractions of each component and the mixture, and went on for finding the equilibrium constant when delta G naught is known, and when heterogeneous things are also there, how to find out this, okay? And later, when we know K at one temperature, how to find the K at another temperature, okay? When K is known, what is the extent of the reaction we know, okay? How is K known, delta G naught is known. So finally, at some given temperature, okay, at a given temperature, there is some specific delta G naught, and that delta G naught determines the equilibrium constant. Now, based on that, we will say extent of the reaction. So, for any reaction you take, based on a temperature, you will have this much maximum conversion of the reactant. Okay, that's all for today's week. We'll meet in the next session on 18th evening, 6:30. We'll be discussing the summary of all the course, and we can discuss few exercise problems from all the assignments to get a summarized version of the whole course, and it will be easy for you guys to prepare for the exam. And I wish you all a very, very all the best for the exam. Okay, thank you.